Hello everyone. So we have been given this stress field here, and we've been asked to find its principal stresses as well as their corresponding directions. And we've also been asked to essentially use Mohr circle to verify our results. So essentially what we can start out by doing is we can put these 6 stress values into its stress field format, which is essentially this right here. Now notice with our stress matrix or our stress field, it's going to be symmetric about our diagonals such that tau xy is equal to tau yx. So that's a very handy feature. So that's why we can say that tau xy is equal to 2 as well as tau yx is also equal to 2. So we're basically just taking these 6 values and then plugging them into their corresponding spot. So now, you might be wondering how we can find a principal stress. Now, if you've taken essentially the eigenvalue before of a matrix, this is pretty much the same exact process where we take the determinant of the given matrix that we have subtracted by some placeholder value times the identity matrix, and then we solve for the characteristic equation. Now, if you haven't done that before, no worries. We're going to walk through it pretty much right now. So we can start out by writing the determinant of this sigma matrix here, or our stress field. And we're going to subtract by a placeholder value called sigma bar. Now, sigma bar is essentially going to be our eigenvalues later on that we're solving for. And we're going to multiply sigma bar by the identity matrix, which in this case is going to be a 3 by 3 matrix. So it fits the same dimension that we have for our stress field. And then what we can do is essentially start plugging stuff in. So we'll have 4 minus sigma bar, 2, 0. We'll have 2, and then 3 minus sigma bar, and then 0, and 0, 0, and minus sigma bar. Now, I'm going to leave out the units for megapascals, I know, but I'll put them back later. So we have that in the correct terms. And then we'll essentially set our determinant equal to 0. So now the next step is to solve for the characteristic equation. And essentially what this means is solving out for the determinant. Speaking of which, I need to add determinant. There we go. Okay, so by taking the determinant, so we'll have our 4 minus sigma bar, and we'll have 3 minus sigma bar, and then minus sigma bar. Then we'll have minus 2 times 2 times negative sigma bar, and that'll be equal to 0. So now what we can do is we can start to factor stuff out. So we can pull out a sigma bar, and then we'll be left with sigma bar squared minus 7 times sigma bar plus 8, and this will all equal 0. So we can say one of our essentially eigenvalues, sigma bar, is going to be equal to 0. And one thing we can actually say off the bat by looking at our matrix is we have these zeros here, and we have this sigma bar all alone. So essentially that'd be a direct indicator that we will have a sigma equal to 0. So that's kind of a neat handy feature for different essentially eigenvalues on your diagonal. But anyways, unfortunately we cannot factor this piece here right off the bat, so what we're going to have to do is we're going to have to solve for it using the quadratic function or formula. So we'll have, that'd be positive 7, and then plus minus, so we'll have 49 minus 32, and that'll leave us with 3.5 plus or minus 1/2 times radical 17. So we'll get a sigma bar equal to 1.43845, and we'll get another sigma bar equal to 5.56155. So we pretty much found all of our principal stresses, but now we have to label them properly. Now, we're going to have a sigma 1, we're going to have a sigma 2, and we're going to have a sigma 3, essentially one corresponding to each eigenvalue that we found. Remember, we have the 0, the 1.4, and then the 5.5. So essentially, sigma 1 is going to be greater than sigma 2, and sigma 2 is going to be greater than sigma 3. So by this standard, we can say that sigma 1 is going to be equal to 5.56155. Sigma 2 is going to be equal to 1.43845. And sigma 3, I'm going to try to squeeze it, and here is equal to 0. Perfect. And now we can circle that. Okay, so now for finding directions, I'm going to walk us through how to find all three of our directions. So the first one up is going to be sigma 1. So we can let sigma bar be equal to sigma 1, which is equal to 5.56155. And pretty much what we're going to do is we're going to take this matrix right here. Before we took the determinant, we're going to take this matrix, and what we're going to do is we're going to multiply by some normal vector consisting of nx, ny, and nz, and we're going to set this equal to a 0 vector, essentially a 3x1 column vector just full of zeros. And then we're going to solve for nx, ny, and nz. So let's start doing that. So what I'm going to do is go down here. So first up, we had 4 minus our sigma bar value, but now we're saying sigma bar is 5.56155, which is equal to sigma 1. So that will leave us with negative 1.56155. And then the 2 is unaffected, 0 is unaffected, 2 is unaffected. Now the next value we had was 3 minus sigma bar. So I'll leave us with negative 2.56155. We'll have 0 unaffected, 0, 0. And then we had just negative sigma bar. So it'll just be the negative 5.56155. And then this will be multiplied by that normal vector that I was talking about, nx, ny, and z. And that'll be equal to a 0 column vector. Just like that. So now what we can do is we can essentially solve across and solve this system of equations. So this first system that we have, let's say this, so we'll have negative, and then that'll be multiplied by nz, which will be equal to 0. So off the bat, we can say that nz is going to be equal to 0, and that's all right. Now, for the next one, we essentially multiply across, and we get plus 2n sub y, and that is going to be equal to 0. And we'll pretty much do the same thing for the other equations. So there's a lot of multiplying across with matrices. So we're going to get a lot of practice with that tonight. Okay, so now we have these equations. And then, in fact, with this first one, what I'm going to do is I'm going to isolate it and then solve for nx, simply by dividing by negative 1.56155. So we get nx is equal to, essentially we'll have to add it over and then divide by the 1.5. So we'll get 1.28078 n sub y. Because then what we can do is we know with every single normal vector, if you were to take, or unit vector per se, so you have your nx squared plus ny squared plus nz squared, and this must be equal to 1, because all unit vectors must have a magnitude of 1. So now before we said that n sub z is going to be equal to 0, so obviously this term can just drop out right off the bat. That only makes our lives easier. And then we can plug in n. So if we essentially square this 1.28078, that'll give us 1.6404 ny squared plus ny squared is equal to 1. So then we can essentially solve for ny, and that's going to be equal to 0.61541, and then nx is then going to be equal to 0.78821. And that is the first direction for sigma 1. So now we can solve for sigma 2. So I'll grab a different color here, and we'll say sigma bar is going to be equal to sigma 2, which is equal to 1.43845. and we'll pretty much solve in the same format that we did before. So we'll set up our matrix, we'll do the subtraction, and we'll essentially keep on going through. Okay, so once we subtracted our diagonal by sigma 2, then we'll set up a fresh unit vector here of nx and y and z, and that'll be equal to our 0 column, 0, 0, 0. Now, nz again is going to be equal to 0, because otherwise we'll have some coefficient times nz equal to 0. And since the coefficient isn't 0, then that means nz will have to be 0, which again is all right. And then we'll essentially multiply the first two rows like before. So we'll get 2.56, 155, and x plus 2 and y, that'll be equal to 0. And we'll have 2 and x plus 1.56, 155, and y also equal to 0. So now we'll do something similar where with this first equation we'll solve for an x, and that will be equal to negative 0.78078 n sub y. And then like before, we're still going to have the nx squared plus ny squared plus nz squared, because that relationship is the same. It's going to be equal to 1. And that's because essentially n is a unit vector, and all unit vectors have a magnitude of 1. And then what we can do is nz is going to be equal to 0, so we can cross that out, and then we can substitute for n sub x. So that'll give 0.60961 ny squared plus 1 times ny squared equal to 1. So that will give ny as 0.78821, and then nx will be equal to negative 0.61541. And that is 2 in the bag. One more to go. So now, this should be getting familiar. We can say sigma bar is equal to sigma 3, and then we said before sigma 3 is equal to 0. So now we can fill out the matrix, and it'll pretty much be its matrix as we started, because we're not subtracting anything now. And then we'll multiply by our column vector of the unit vector n, and then we'll have the 0 vector, just like that. So now what we can say is this bottom one, so we'll have 0 times nz equal to 0, and then we'll have 4 times nx plus 2 times ny is equal to 0. But then we'll also have that 2nx plus 3ny is equal to 0. So now in this case, what's going to actually happen is nx is going to be equal to ny, which is going to be equal to 0. And that is going to leave nz to be equal to 1. Because notice with the other cases here, we had some coefficient times nz equal to 0. So that forced nz to be equal to 0. But now in this case, essentially what we are left with is now we have 0 right off the bat. So nz can be non-zero in this case. And now especially, this is a little hint, since our sigma is going to be equal to 0, that's actually going to force nz to be equal to 1, because our essentially third eigenvalue is going to be out of the page. Because remember, with our eigenvalues, they're going to give us, in three-dimensional systems, they're going to give us 3 different eigenvalues with 3 different directions. And now these eigenvalues, they have to follow, or I should say these eigenvectors, they have to follow the right-hand rule, where they're all perpendicular to one another. So notice if I were to write these out. Right, so let me write these out real quick. So if we say sigma 1 as a vector here. Let's do this. If we say sigma superscript 1, right? So we'll essentially take the sigma 1 vector. Before, we said that was 0.78821. Sorry for the scrolling. 8821. And then we said that the in y component was 0.61541. So we have 0.61541, and the z component was 0. Now, for the sigma 2, for that, we said the direction was negative 0.61541. The y component was 0.78821, and then z was 0. And then for the third one, sigma 3, well, we want to say that that is 0, 0, 1. So, essentially with traditional vectors, so if you have, or traditional three-dimensional coordinate systems, if you have your x, your y, and your z, when you essentially take the right-hand rule, that's kind of I guess a way to visually see where your third dimension will be. That's often used with cross product or finding the curl, but anyways, they're all perpendicular to one another. And the way we can test this is by doing the dot product. So if you were to essentially take the dot product of 1, or sigma 1 with sigma 2, you're going to have 0.78821, because you're multiplying your x components first. We'll have negative 0.61541, and then you'll plus 0.61541, because now we're multiplying our y components together. We'll have 0.78821, and we'll have just plus 0. And this will actually equal 0 in the end, which is what we want, because both of these are perpendicular to one another. So that's actually why with sigma 3, we have to say that nz is equal to 1, and nx and ny are equal to 0, such that all of these would be perpendicular to one another, such that if sigma 1 times sigma 3, that'll equal 0, and then sigma 3 dot product with sigma 2, that will also equal 0, because then this will satisfy our principal coordinate system. So pretty much what we can do, now that we have our eigenvalues and we have our directions, now what we can do is we can set up Mohr's circle to then verify our results. So let's do that now. So we can start out by drawing a coordinate system, and this will be our shear stress axis. This will be our normal stress axis, and we'll draw a circle here. Here, I'll shrink this a little bit. Okay, so on this side, we will have sigma 2, or actually, let me call this sigma max, just so we don't get it confused with our eigenvectors, or eigenvalues, and we'll have sigma min on the other side. So now, what we can do is we can first calculate the center. Now, the center of our circle is going to be equal to the original sigma x plus sigma y divided by 2. So now, sigma x from before we said was 4, and then sigma y we said was 3. So we can go back down here, and then 4 plus 3 is 7, divided by 2 gives us 3.5. So on the circle, roughly in the center, we can mark 3.5. So offset that off to the side a little bit here. Okay, so now the next thing that we can calculate is the radius. So the radius is going to be equal to sigma x minus sigma y divided by 2 squared plus tau xy squared. And then we'll just take the square root of that. So we said from before, so sigma x was 4, sigma y was 3, so we'll essentially have 1/4 plus tau xy, and from before tau xy was 2, so 2 squared will give us 4, and then we'll take the square root of that, which will give 2.06155. So now, what we can do is we can actually plot our points here on our circle. So remember, so we had a sigma y of 3, and then we had a tau xy of 2. Now remember with this axis, so this will be the negative tau side, and this will be the positive tau side. So I know it's flipped from normal convention, but that's so our typical sign convention will then stay true. Otherwise, that will be a little bit different from what we'd anticipate. And then on the opposite side here, we'll have our sigma x value, which was 4, and we'll have the negative of our tau xy, which tau xy was 2, so we'll have 4, negative 2. So now, what we can do to calculate this sigma max and sigma min is we can essentially say that sigma min is going to be equal to the center minus the radius, and then sigma max is going to be equal to the center plus the radius, right? So we're starting at the center, and then we're going radius out, or we're going a radius distance back. So if we do C minus R, we'll get 1.43845 megapascals. And if we do C plus R, we get 5.56155 megapascals. Now you might be thinking, wait a second, these are familiar. And if you're thinking that, then that is right, because if we actually scroll back up here, we can see that 1.43845 was our sigma 2 eigenvalue, or principal stress, and then we had 5.56155, which was our first principal stress that we had. So this is actually the maximum principal stress, or the maximum normal stress that we have, and then this is the minimum normal stress that we have. So now you might be thinking, so Mohr circle, so it looks like this is two-dimensional, right? So where's that third dimension going? Well, that third dimension, right, because we said in the z direction, so we have a, you can imagine essentially going in or out of the page, we have a vector 0, 0, 1 corresponding to this essentially principal stress equal to 0. So that's kind of a walkthrough of how we can essentially take a stress field, we can find the eigenvalues as well as their corresponding eigenvectors, and then we can translate it back to Mohr circle to actually double check our work and make sure that we get the same results. So this is definitely a very handy walkthrough. I know it was a long video, but it's a very important basis to essentially build upon for future studies.